All right, for the lives of stars, just keep in mind that this is a theory. We talk about the birth of a star, but nobody has ever actually seen it. So this is just all theoretical ideas of scientists. Okay? All right. The supernova of 1054. In the summer of 1054, some Chinese astronomers noticed a guest star in the night sky. The star was so bright people could see it during the day. The star remained visible for almost 2 years. How did these ancient astronomers interpret it? Was it a sign that the emperor would be visited by an important guest? People from around the world recorded and interpreted the event differently. Almost 1,000 years later, scientists realized the guest star was the explosion of a giant star 4,000 light years away. So powerful was the explosion that all life within about 50 light years would have been wiped out. Now called Supernova 1054, its remains are known as the Crab Nebula. All right, so why was Supernova 1054 so notable? And how do you think ancient astronomers might have interpreted the event differently than astronomers today? All right, how does a star form and what determines its lifespan? Stars do not last forever. Each star is born, goes through its life cycle, and eventually dies. Of course, stars are not really alive. The words born, live, and die are just helpful comparisons. A star is born when the contracting gas and dust from a nebula becomes so dense and hot that nuclear fusion starts. How long a star lives depends on its mass. All stars begin their lives as parts of nebulas, such as the one in Figure 1. A nebula is a large cloud of gas and dust spread out in an immense volume. A star, on the other hand, is made up of a large amount of gas in a relatively small volume. In the densest part of a nebula, gravity pulls gas and dust together. A contracting cloud of gas and dust with enough mass to form a star is called a protostar. Proto means earliest in Greek, so a protostar is the earliest stage of a star's life. Recall that nuclear fusion is the process by which atoms combine to form heavier atoms. In the sun, for example, hydrogen atoms combine to form helium. During nuclear fusion, enormous amounts of energy are released. Nuclear fusion begins in a protostar. All right, so describe a nebula and tell what happens there. All right, lifetimes of stars. How long a star lives depends on the star's mass. You might think that stars with more mass would last longer than stars with less mass, but the reverse is true. You can think of stars as being like cars. A small car has a small gas tank, but it also has a small engine that burns gas slowly. A large car has a larger gas tank, but it also has a larger engine that burns gas rapidly. So the small car can travel farther on a tank of gas than the larger car. Small mass stars use up their fuel more slowly than large mass stars, so they have much longer lives. Generally, stars that have less mass than the sun use their fuel slowly and can live for up to 20 billion years. A medium mass star like the sun will live for about 10 billion years. The sun is about 4.6 billion years old, so it is about halfway through its lifetime. In Figure 2, the yellow star is similar to the sun. Stars that have more mass than the sun have shorter lifetimes. A star that is more massive than the sun, such as the blue star shown in Figure 2, may live only about 10 million years. That may seem like a very long time, but it is only 1/10 of 1% of the lifetime of the sun. All right, so the yellow star has much less mass than the blue star and so will live longer. Explain why. All right, how does a star form from a nebula? What factor determines how long a star lives? A star is twice as massive as the sun. How will its lifespan compare? So get those questions answered. All right, what happens to a star when it runs out of fuel? When a star begins to run out of fuel, its core shrinks and its outer portion expands. Depending on its mass, the star becomes either a red giant or a super red giant. Red giants and super red giants evolve in very different ways. After a star runs out of fuel, it becomes a white dwarf, a neutron star, or a black hole. White dwarfs. Low mass stars and medium mass stars like the sun take billions of years to use up their nuclear fuel. As they start to run out of fuel, their outer layers expand and they become red giants. Eventually, the outer parts grow larger still and drift out into space, forming a glowing cloud of gas called a planetary nebula. The blue-white core of the star that is left behind cools and becomes a white dwarf. White dwarfs are about the size of Earth, but they have about as much mass as the Sun. A white dwarf is about 1 million times as dense as the Sun. White dwarfs have no fuel, but they glow faintly from leftover energy. After billions of years, a white dwarf stops glowing, then it is called a black dwarf. All right, so over here you're going to compare and contrast. How does the mass and size of a white dwarf compare with the mass and size of the Sun? Choose one of those multiple choice answers. All right, supernovas. The life cycle of a high-mass star is quite different. These stars quickly evolve into brilliant supergiants. When a supergiant runs out of fuel, it can explode suddenly. Within hours, the star blazes millions of times brighter. The explosion is called a supernova. After a supernova, some of the material from the star expands into space. This material may become part of a nebula. This nebula can then contract to form a new, partly recycled star. Recall that nuclear fusion creates heavy elements. A supernova provides enough energy to create the heaviest elements. Astronomers think that the matter in the Sun and the planets around it came from a gigantic supernova. If so, this means that the matter all around you was created in a star, and all that matter on Earth is a form of stardust. Okay, so supernova remnant Cassiopeia A. Cassiopeia A is the remnant of a once massive star that died in a supernova explosion seen 325 years ago. Explain the connection between your body and a supernova. All right, neutron stars. After a supergiant explodes, some of the material from the star is left behind. This material may form a neutron star. Neutron stars are the remains of high-mass stars. They are even smaller and denser than white dwarfs. A neutron star may contain as much as 3 times the mass of the Sun, but be only about 25 kilometers in diameter, the size of a city. In 1967, Jocelyn Bell, a British astronomy student working with Anthony Hewish, detected an object in space that appeared to give off regular pulses of radio waves. Some astronomers thought the pulses might be signals from an extraterrestrial civilization. At first, astronomers even named the source LGM for the Little Green Men in the early science fiction stories. Soon, however, astronomers concluded that the source of the radio waves was really a rapidly spinning neutron star. Spinning neutron stars are called pulsars, short for pulsating radio sources. Some pulsars spin hundreds of times per second. All right, so up here, fill in the missing stages on the diagram. Now, think about where the Sun fits on the diagram. On the lines below, describe what will happen to the Sun when it runs out of fuel. And then down here, predict. An alien civilization is in orbit around a high-mass supergiant star. Should they stay or should they go elsewhere, and why? All right, black holes. The most massive stars, those that have more than 10 times the mass of the Sun, may become black holes when they die. A black hole is an object with gravity so strong that nothing, not even light, can escape. After a very massive star dies in a supernova explosion, more than 5 times the mass of the Sun may be left. The gravity of this mass is so strong that the gas is pulled inward, packing the gas into a smaller and smaller space. The star's gas becomes squeezed so hard that the star converts into a black hole, and its intense gravity will not allow even light to escape. No light, radio waves, or any other form of radiation can ever get out of a black hole, so it is not possible to detect directly. But astronomers can detect black holes indirectly. For example, gas near a black hole is pulled so strongly that it revolves faster and faster around the black hole. Friction heats the gas up. Astronomers can detect X-rays coming from the hot gas and infer that a black hole is present. So again, they are just inferring that. This is kind of all theory and their idea behind it, but we don't really have proof. All right, review. What determines if a star becomes a white dwarf, neutron star, or black hole? Predict. Which will the Sun become? A white dwarf, neutron star, or a black hole? And why?